This lecture introduces the empirical Bayes method, which is becoming very widely used in traffic safety. And so this will give you some background as to how the EB method compares to some of the more traditional methods we've talked about previously. And so today's content will start by talking about some of the problems with traditional before and after study designs, which were introduced during the last lecture. And then we'll delve into an example of the empirical Bayes method and walk you through procedurally how this method is used in order to develop more precise and reliable estimates of how many crashes we would expect to see in the absence of the application of a specific treatment. Okay. And so we talked about this a little bit last time, but when we're relying on short-term crash counts in order to determine when and where treatments are appropriate for implementation at a given site, there's some uncertainty involved in that process, just given the natural fluctuation in crash data. And so, for example, if we examine data over any individual period, or say a 2-year or 3-year average, we can see significant variability as compared to the long-term average, and that could be due to factors that are completely unrelated to the actual safety of that site in consideration of site-specific factors. And so to that end, in many instances, we just have limited crash data, which potentially complicate our analyses. And so that's what we're going to talk about addressing here. Okay, and so within that context, there are a couple important analytical concerns that arise and create issues if we're trying to work with, say, just a simple naive before and after study design. And one of the most important of those just relates to regression to the mean, which we've introduced previously. And so when we talk about regression to the mean, when we think about safety improvement projects, they tend to be implemented at locations that experience larger than average numbers of crashes. So locations with a crash history. And so consequently, as a function of that, these may be sites that actually do have a documented safety problem, or alternately, they could be, for lack of a better term, normal sites that simply we're observing during a high point in the crash cycle on a year-to-year basis. And so at those types of locations, if we had done nothing whatsoever, we would expect that these high crash sites would tend to regress back towards the long-term average over time. Hence the terminology here, regression to the mean. And as a consequence of that, when we think about trying to evaluate the effectiveness of these different projects, if we're not able to account for that inherent variability and that sort of selectivity bias that occurs, we would tend to overestimate how effective some of these treatments are. Now, there are also some additional concerns that may come into play, and that would relate to contemporaneous changes. And so what we mean by that, once that treatment is implemented, there may be some other differences that occur concurrently that weren't present during the pre-implementation period. And so as an example, here in Michigan, if we go back to December of 2019, we had legalized recreational marijuana at that point. And so if that has safety impacts, that fact would be lost on us if we were conducting an evaluation of crash data for 3 years, prior to a project that was implemented in 2019 or 2020 versus 3 years afterwards. Similarly, if we're in the midst of a pandemic, it's probably not an apples to apples comparison as well. And so if we're just relying on naive before and after study designs, these types of factors are generally going to be lost on us. Now we can address that to some degree by including control groups, as we had talked about during the last lecture. And the empirical Bayes method does something similar, and it basically tries to take information about the sites where the treatments are applied, and then similar information for a control group of untreated sites to give us a more reliable estimate of what we would expect to see in the absence of that treatment being applied, while controlling, to the extent possible at least, for all of these other factors that would also affect safety at these given sites. Okay. And so we've seen this general demonstration before. So if we think about regression to the mean, let's assume we've got 4 years of data prior to when a safety treatment was implemented. If we look at the 3 most recent years, as shown here, that will give us a general estimate of safety performance during the before period. And then let's say we compare with the 3 years immediately after. And so from that, we have, under a naive study design, this general estimate of how effective that treatment is. Now, hypothetically, had we extended that analysis period to 4 years rather than 3 years prior to that analysis, we would instead have seen a long-term average that corresponds to this green line here rather than the blue line as an example. And so we tend to have an upward bias here because we just happen to conduct these observations using 3 years of data during which we saw a larger than normal number of crashes at this specific site as an example, okay? And so consequently, the actual effectiveness of whatever treatment we applied would be the difference between that long-term average without the treatment having been applied to what was experienced afterwards, okay? And so consequently, we're basically overestimating the effectiveness of that treatment by this amount you see right here, if we don't account for that underlying uncertainty and those factors that just relate to us observing crashes during a high point in that cycle, okay? And so this is a particularly big issue when we're dealing with sites like rural roadways where we would have low number of crash counts on an annual basis. And so as an example, we've talked previously about how crash data can generally be characterized as following the Poisson distribution. And so, for example, if we look at the Poisson distribution, we know that it's defined by a parameter lambda, which expresses the mean rate. And in this case, that would be the mean number of crashes per year as an example, okay? And so we know based on the Poisson distribution that interestingly, the mean and variance are equal to one another. And so consequently, we can basically calculate what the standard error would be in terms of the number of crashes per year that would vary from site to site. So basically the variance or standard deviation of these crash counts. And so in this case, if we're observing 100 crashes per year, and that's over a 3-year period, the standard error of that estimate is just going to be whatever the mean number of crashes is divided by our sample size, which in this case is 3. And so consequently, our standard error of that mean estimate of 100 crashes per year is going to be plus or minus 5.7 crashes. And so if we constructed a 95% confidence interval, so for example, multiplied that by 1.96, we see plus or minus 12 crashes per year. So we have reasonably good reliability, 100 plus or minus 12 in terms of the number of crashes per year, okay? Now, in contrast, let's assume that we have a very rural location that experiences only a crash every 10 years. And in that circumstance, if we look at that long-term average and the standard error of the estimate, if we're averaging 0.1 crashes per year over 3 years, our standard error in this case is actually nearly twice what the mean number of crashes is. So this goes past 0, actually. And when we construct a 95% confidence interval, so we double these bounds, and you have a very large interval, and it becomes very challenging for us to be able to determine whether or not there's a statistically significant difference in crashes between the before and after periods, okay? And so what we try to do is use these more sophisticated methods, particularly when we have either very limited sample sizes in terms of the number of sites or the number of years of data that are available to us, or if simply the mean number of crashes we'd see year to year on a site-specific basis is small. Because in those circumstances, if we see a regression to the mean effect, it's going to be very large just relative to the underlying uncertainty. As we get larger number of crashes, so particularly at high volume sites as an example, that inherent variability tends to be less, and regression to the mean as a consequence tends to be less severe in those instances. And so this is a particularly big problem with small samples in various definitions, okay? And so as we think about trying to forecast safety performance, oftentimes we're dealing with short-term crash history, so a 3 to 5 year period. We could go back longer, 10 years or more, but as we had talked about last time, there are some limitations that arise to that end. Long-term crash records may not be available. Now, that's less of a concern in modern times with our available crash databases. However, it can be a concern, particularly if we think about local agencies who simply may not be maintaining that data over time. And then, as alluded to previously, if the average crash frequency per year is low, even that long-term average may tend to be imprecise. And so beyond that, as we extend the analysis period, we generally don't do quite as good of a job in our databases of tracking what changes have occurred over time. So generally, road agencies would have very good asset management inventory databases for whatever the current status is of the road network. But if we ask for a similar snapshot 3 years ago or 5 years ago, we would tend to have less reliability there. And as an example, here in Michigan, the DOT has basically retired its prior sufficiency file that maintained a lot of this inventory information. And so now if we try to make comparisons over time, these roadways have been segmented in a different manner, and it's not a simple apples to apples comparison. And so these are a few of the types of issues that become problematic over long time periods. And so another advantage of the empirical Bayes method is that we can address this underlying imprecision in our crash data while also doing so with a relatively smaller sample size of crashes, okay? And so to overcome this, one reasonable approach is we get crash data for sites that are similar in virtually all respects, and we use those as a control group. So in that instance, we're basically increasing our sample size while minimizing concerns as to some of those other spurious factors that may be due to changes that have occurred over time ultimately, okay? And so in the empirical Bayes approach, similar to what we saw with the before and after with control, we have some number of crashes that were experienced at a project site during the before period. That site was probably selected at a high cycle in crashes. And so if we think about similar locations, those are probably clustered somewhere below. And so when we're trying to assess how effective a treatment is, it's probably more appropriate to calculate a weighted average between what's been experienced at that site of interest where the treatment has been applied and what's been experienced at similar sites. And consequently, we would come up with a better and more accurate estimate of the crash reduction if we're able to effectively leverage such an approach, okay? And so that's what the empirical Bayes method does. And so you may have some degree of familiarity with Bayes' theorem from probability and statistics, but basically what we're aiming to do here is make use of existing information we have based on historical data, and we're using that to compute a weighted average based on information about those control sites and the sites where our treatments are actually implemented. And so from that standpoint, there are a few primary advantages of using the empirical Bayes method. Now, first and foremost, it allows us to explicitly account for a regression to the mean and allow for a more precise estimate of those effects. Likewise, we're able to more accurately estimate other parameters of interest to us, and that would include not just the average number of crashes per year, but the variability we would expect to see on a year-to-year basis. And so we'll see improvements from that perspective with the empirical Bayes as well. And then beyond that, we also allow us to control for some of those potential biasing factors. So the legalization of marijuana or the onset of a pandemic or things that would affect traffic beyond just the site characteristics. And so if we consider the effects of those confounds on the treatment site and the control sites simultaneously, we can kind of tease out and control for that effect. And as a consequence, come up with a more reliable estimate of what the actual impacts on safety would be. Okay? And so again, the primary advantage of the empirical Bayes method is that we're explicitly accommodating for regression to the mean. And so back to Bayes' theorem, what we're basically doing here is we're taking information about a reference population, or in this case, a control group, with crash history related to our individual treatment site. And so as illustrated in the preceding diagram, we're basically calculating a sort of weighted average of the site-specific data with data from a control group that's otherwise similar. And so that basically allows us to estimate how many crashes would have occurred before implementation of the treatment in consideration of that long-term average. So we're basically mitigating the concerns as to being at a high point in that cycle of crash occurrence from year to year, okay? And then likewise, we can take information from that untreated control group and we can use that to forecast how many crashes we would expect to see in the future. So as traffic volumes change or as the pandemic onset occurs, we'll be able to capture the differences in crashes that were experienced in the control group. And we would presume if the treatment hadn't been applied, we would see those same differences in the treatment groups. And so thereby, we're basically coming up with a weighted estimate that is based upon these broader trends that wouldn't be possible under a simpler, naive before and after study design. And so to that end, there are a few important factors to consider here. So what we're doing here essentially is we're using that reference population to come up with a more reliable estimate of crashes we'd expect to see beforehand. And so in doing that, we're collecting information from sites that have the same characteristics. So, for example, we compare two-lane rural highways with other two-lane rural highways. We compare signalized intersections with other signalized intersections. And so we have that information in the crash history from similar control groups. And then we would have similar information for the site where that treatment is actually applied. And what we're looking to do ultimately then is to develop a weighting factor to determine how much emphasis we should put on the data for the actual site where the treatment has been applied versus data from the control group. And so to that end, we'll want to think about the distribution of these data from site to site and consider how variable our crash data are within an individual site and then across groups of similar sites. And we'll walk through that on some of the subsequent slides here. And so an important consideration here is selecting that reference population. So as I had alluded to previously, if we're looking at urban signalized intersections, it would probably make sense to use a control group that also includes urban signalized intersections and not include a more diverse group there. So we wouldn't necessarily want rural intersections in there. We wouldn't want other types of traffic control. Because occasionally you'll see in the research literature, you could argue that these groups are constructed too broadly. And so, for example, if we used a reference population of all intersections, urban signalized are typically going to be among our highest crash locations. And so if we were to include other types with lower crash risks, we may go the other way and actually underestimate the effectiveness of some of these treatments. And so consequently, when we select these control sites, we'll want to carefully match those based on important characteristics that could include type of traffic control, traffic volume, cross-sectional characteristics, etc. And then a related concern, when we look at these data, we'd ultimately want to consider data from the treatment and control groups over similar time periods. And that relates back to my preceding point in that if you're using, say, control data from 2016 to 2019, we might not see those same trends from 2020 and beyond due to COVID and other factors that would be different in some meaningful way. Okay, so just a few important factors to consider when we're trying to conduct these types of assessments. Okay. And so the use of that reference population is important to us because what it's basically allowing us to do is, if not necessarily eliminate, largely mitigate that regression to the mean effect that we'd be exhibiting as seen on the preceding slides. And so the way we do that is by basically trying to come up with an estimate of the mean and the variance of how many crashes we would expect to see at a given site. Now, contemporary practice, as per the Highway Safety Manual, we would rely on a safety performance function to that end, so basically an empirical regression model. But today we're going to start a little bit simpler than that, and we're just going to look at mean values, mean numbers of crashes across groups of similar locations, and we can extrapolate that and expand to a more rigorous statistical analysis subsequently, but we'll start things off here relatively simply, okay? And so to that end, here we have crash data for a series of 10 locations. And so at each of those 10 locations, We have estimates of the daily entering volume at that site during each year of our 2-year analysis period. And we also have the number of crashes that occurred at each site during those respective periods. And so we're going to start really simply here, and we're just going to calculate average crash rates for any individual location I here. So in this case, I is ranging from 1 to 10. We've got 10 sites. And at each of those locations, we have 2 independent estimates, essentially, of the crash rate at that location. So in year 1, we can take the number of crashes, and all I'm doing here is basically normalizing. So this is giving us crashes per 1,000 entering vehicles per day. Now, traditionally, we've looked at crash rate per million VMT, and so this is largely just for demonstration purposes, but if we were to calculate the data in that manner, the only difference here is that we'd have a 365 on the bottom. We'd obviously have a million at the top instead of 1,000, but those factors are just going to wash out in any case because we're applying that same factor across each of the sites. So this is just to keep the numbers nice and simple largely. And so we can use that same approach. And in these cases, we're just calculating a weighted average. So crashes per 1,000 entering vehicles in each of those 2 years. And we're just doing a straight line arithmetic average here of those. Okay. And so consequently, what we see here are basically average estimates of crashes on a site-by-site basis using a sample period of 2 years of data ultimately. And so as you'll see here, those values range from a low of 0.41 crashes per 1,000 entering vehicles to a high of 1.66. And we see a bit of variability from site to site. And so from our perspective, a fundamental question here is, well, how good are these site-specific crash estimates in forecasting performance? And can we use information from the other 9 sites to improve the estimate of what we would see at that individual site? And so that's what we're trying to do with the empirical Bayes method from a big picture perspective, okay? And so as a starting point, if we think about the number of crashes, so our Y sub ij, so the number of crashes that are occurring at location I during year J, those data are going to follow some distribution. Maybe it's Poisson, maybe it's something else, but the mean number of crashes at that location in a given year is a function of some long-term average, which we can try to specify. And its variability, we're going to denote as sigma squared, and I'm going to note WI here, meaning we're looking at the within location variability, okay? And so that's what the W stands for here, is we're looking at variability within that site. And so this is capturing the variance from year to year within each of these individual sites. So each of our sites I will have its own unique internal variability in year-to-year crash counts, and it will also have its own site-specific mean number of crashes, okay? Now that mean number of crashes is simply going to be a function of whatever the long-term rate is at that location. So in our case, we had an average crash rate based upon 2 years of data. And so we would take that average crash rate, multiply by whatever the corresponding daily entering volume is, and then that would give us the number of crashes we would expect to see at location I during year J. Okay, so we assume this average crash rate is constant at site I over each of the J years, and then our daily entering volume is going to be unique to each location and year, okay? And then in addition to that, that expected crash rate that we see here is going to be a function of the long-term average. And so if we look across all of our sites, including the whole control group, those would have a long-term average, which we could denote as mu. And that quantity would tend to vary across sites. And the B subscript here means that we're talking about the between site variability. And so this is assessing, rather than the variance within an individual site over time, this is the variance across locations, okay? And so consequently, we can then determine the crash rate for our control group of interest is basically going to correspond to this value of mu for whatever the corresponding traffic volumes are, okay? And so what we're doing here is we take Bayes' theorem And we're ultimately interested in estimating an improved estimate for crash rates or number of crashes at the specific intersection we're interested in examining, okay? And so that's going to be a function of two factors. So first of all, the mean number of crashes at a control group, as well as the mean number of crashes we see at that individual site as it relates to that average across the control group, okay? So there's basically two different estimates here we're concerned with, and that's the average at that specific location and then the average at all locations. And so by rearranging this, what we basically see is in the empirical Bayes method, we're calculating a weighted average between the number of crashes or the rate of crashes we'd see at our control group of locations and at our individual crash site, okay? And so here our weighting factor phi is basically telling us how much emphasis we're putting and how much relative weight we're putting on the data that we're actually observing at the location where the treatment has been applied versus the amount of weight we're applying for a control group of similar locations where that treatment hasn't been applied. And so keep in mind, we're just focusing on the data for the period prior to that treatment being applied here. And so that weighting factor is basically going to be a function of how much variability we see between sites versus how much variability we see within individual sites, okay? And so the general rule here is the greater variability we see between sites, that means, you know, you've got 10 locations and you might see quite a bit of variability. So let's say the standard deviation is 5 crashes per year or 10 crashes per year across those different locations. And we would compare that to the average of our within site variabilities. And so at an individual location, maybe we see that same variance of 5 to 10 crashes per year, or maybe we see something that's smaller or larger than that quantity. And as a general operating rule here, the more variability we see across sites or between sites as compared to the total variability, we would tend to give less weight to the control group if there's greater variability, okay, across those sites. And so if in contrast, we saw that the number of crashes were relatively consistent from site to site, and we tended to see significantly more variability within the sites, then we would tend to give more weight to that long-term average and less weight to the data for that individual site, okay? And so when we think about this in concept, generally the way it works is we are thinking about how reliable that control group information is relative to the reliability of those site-specific estimates. And so as the data becomes more reliable or more precise for our individual location, we apply more weight to that estimate. And as our data become more reliable for the control group or less reliable for our individual site, we're applying more weight to that control group's data, okay? And so here we just see nice simple calculations for how we obtain those variance estimates. And so the within site variances are just calculated as shown here. So in this case, we only have 2 years of data, so it's relatively simple and straightforward to calculate. For each of those individual years, we take the difference between that year's crash rate and the long-term average. We square that quantity, sum it, and then divide it by n minus 1, where in this case, n is the number of years of data we have for that individual location. And so that gives us an estimate of the year-to-year variability, again, within location I. And then the between intersection variance is simply going to be an estimate of whatever the long-term average is of those respective sites compared to the average across all locations. So what we're doing here, we're taking the site-specific average minus the average across all locations, squaring that quantity. And in this case, we're dividing by I minus 1, where I is the number of intersections, okay? And so from here, we basically have 2 independent estimates of variability, one which is reflective of the variation in crashes from year to year at the site where the treatment has been applied, and a second that's due to the variability across locations over time, okay? And so as an example, taking the same data we had demonstrated precedingly, for location 1, we see within location variance of 0.95. And if we take the other control locations, we see between site variance of 0.21, okay? So in this case, we find that there's significantly greater variability within our site versus between our sites. And so consequently, in calculating that weighting factor, we'll expect that in this instance, our phi will be relatively small. And so in this case, 0.55. And so as a consequence of that, since we're seeing relatively small variability between sites, we're giving a reasonably large amount of weight then to the data for the mean value of those control sites. And so in this case, it's nearly uniformly distributed across the two sources. And so we give a weighting factor of 0.55 to our site-specific estimate. We give a weighting factor of 0.45 to that long-term mean. And so our average estimate then is going to be 1.06. Now, in this case, those estimates aren't particularly far off from one another. So the long-term average across all sites was 1.07. At that individual site was 1.05. And so we're roughly right in the middle in that case. And that's going to be fairly typical, where it will come close to an average between the control group data and the site-specific data. And this is just demonstrating site by site. You will notice here, what we'll generally see is that the locations that have crash rates that are nearest to the mean across all sites, so for example, site 1 at 1.05, site 7 at 1.05, in those cases, the EB estimates aren't very different at all from what we would see from just the naive before-after type study design. It's in those extreme cases where we're at 1.66 or 1.56, where those effects are dragged closer to the mean. And so this would tend to be, if we extended this period beyond 2 years to 5 years or 10 years, these would probably be more reasonable estimates of long-term crash performance than this 2-year sample. Likewise, the same is true on the lower side of the spectrum. So if we're at 0.6 or 0.75 crashes per year, we also see relatively large differences where those means are being dragged upwards towards the mean, because those sites tended to experience lower than average crashes. And so as an example, if we think about the speed limit increase example we had talked about previously, maybe we had selected sites that had low numbers of crashes at which to increase speed limits. And so consequently, we may be underestimating the number of crashes during the period before those increases went into effect. And so the EB method can account for variations in either the higher or lower extremes, as the case may be, okay? And so this plot here basically just demonstrates our site-specific rates. So under naive before and after study design, this is what those estimates of the crash rate would be. So they ranged from just over 0.4 to nearly 1.7 crashes per thousand entering vehicles. The green dots here basically demonstrate what the values were for the reference or control groups for those same sites. And so, for example, in this case, the sites that were in that range of 0.4 crashes per thousand entering vehicles, the control site showed a rate that was significantly higher than that. So on the neighborhood of 1.1, 1.15. And then similarly, on the other end of the spectrum, the sites that experienced a crash rate of 1.65, 1.7 crashes per thousand entering vehicles, the control sites experienced significantly fewer crashes in that context. And so when we calculate a weighted average, what we'll tend to see is near the mean, this EB estimate, so the blue you see right here, falls very close to what we'd see from the naive before and after study design, which is represented by the red line. And the further we get from the mean in either direction, the more variability we see, okay? And so the same general phenomenon is going to hold more broadly. And so this gives us at least a high-level introduction to what we would expect to see through an empirical Bayes type analysis, okay? And so if we think about this in terms of the weighting factors, this is just expressing to us how the within site variability matters, okay? And so the lesser that within site variability is, as you can see here, the higher the weighting factor that we would apply, then the larger our value for phi. And in contrast, as that variability gets larger and larger, we're applying less and less weight to that estimate accordingly, okay? And so as we think about this, that with insight variance, as you'll recall, is basically taking our crash rate from year to year and dividing by the number of years of data we have. And so the more data we have available to us, the lower this with insight variance is going to be. And then as a consequence of that, we would tend to apply greater weight in those circumstances to our data for that specific site, for example, okay? And so that is a very quick introduction to the empirical Bayes method. When we come back for the next lecture, we'll work through some additional examples, and that will include using an SPF example table from the Highway Safety Manual. And so ratcheting things up a notch, but basically what we'll find is that the simple methods that were introduced today will parallel very nicely as we increase the complexity in terms of the statistical methods that are being applied. And so that wraps things up for today. We'll also have a homework assignment that will be posted in short order, and I will talk to you both next week. Thanks.